Hello everyone. Let me swap the screen. Yes. Could one of you tell me Hello everyone. Oops, let me mute my YouTube link. Okay, could one of you tell me if the sound and video quality are both fine? Waiting for the feedback, then I will start. Any issues with sound or video quality? Okay, thanks Furkan. Then let's start. Let me fit my video there. The top right corner. Yes. Okay, I think we are good. So today, as of 27th of November 2024, we are together with the 9th lecture of our FPGA from Zero to Hero in English series. So agenda is as follows. We will first go over purpose of that reset signals. Then we will be discussing some reset code examples. Next, third one will be reset architectures and infrastructures. Then we have some slides regarding asynchronous reset, synchronous reset, and not using reset comparison slides. So some pros and cons will be discussed. In case you have some questions, don't hesitate to ask using the chat window. I will also try to check the chat window during the stream. But anyways, at the end we will have a wrap up and a short Q&A. Also this Sunday, that Europe time, it is like Greenwich Mean Time +2 right now. Actually, it is always like that, this location, but it is not summertime now at least. So that GMT +2 time zone this Sunday at 10 a.m. we will be having a Q&A session of this lecture. We will similarly, of course, a little bit fast go over these slides and then try to answer specific questions regarding this class or any other FPGA related questions. Okay. Let's start with the first slide. So, purpose of reset signals. These reset signals provide initial value of sequential cells in hardware. So they are quite important, and in some scenarios actually you need them there is no way to skip them. I will give some more specific examples in next slides, but that general purpose is making those registers, in other words, flip-flops, start at a known state after the device configuration. So this is the major purpose, like these first two bullets actually summarize that. What happens that initial value is not specified using a reset? Actually, it little bit depends on the technology you are using. Also, the commands you provided in your HDL file. So hardware description language file. So if either you are using VHDL or Verilog or SystemVerilog, so there are some ways. Actually, you are using column equal sign to set up an initial value. But for flash-based FPGAs, for instance, those setting init value stuff is not working properly. So actually, that is one of those scenarios that when you are using flash-based FPGAs, you need to be more careful about some points during design and verification compared to RAM-based FPGAs. So this is the technology dependency is important. So, but what happens if you are not using a reset and you didn't use a colon equal initial value after that signal or variable definition? Then these sequential primitives are assigned to a default value. So it is like for RAM-based FPGAs, it is 99% of the time 0. But as I mentioned, this statement is not valid for flash-based FPGAs. Let me little bit make my video smaller so you can see the whole slides. Yes, it is better right now. So what was I saying? Yes, this starting with the default 0 value, it is almost always the case for RAM-based FPGAs, FPGAs with transistors with actually RAM cell technology. That is the case. But I was saying this statement is not valid for flash-based FPGAs. So such FPGAs, such flip-flops keep their values after power off. So like they are actually, as you know, flip-flops are able to keep that last assigned value after the rising edge of clock or falling edge of the clock. So they are edge sensitive primitives and they are capable of keeping that value, unlike that level sensitive latches. But flash-based ones, actually, they are capable of keeping their values because they are behaving like non-volatile memories. So this is unlike RAM-based technologies, FPGAs or SoCs. So this is a major difference. So one designer, verification engineer shall be aware of this difference and act accordingly. So yeah, as I mentioned a few minutes ago, in most cases, default value is logic 0 in RAM-based FPGAs. But there are also some exceptions for that. So their default value is like 1. Actually, I grabbed this part from one of Xilinx ultra scale plus guidelines. So that's Xilinx FTSE, and second one is also Xilinx. I forgot to add Xilinx at the beginning of this tick. So this FTSE and FTPE, these primitives, their default value, output default values are 1. So that you need to check actually to be able to aware of such cases. You need to read FPGA vendors you are using family guidelines. Let's say you are using Vertex 7, then you need to check those data sheets regarding that are providing some general information about that family. Also, in most cases, there are good design guidelines for each and every vendor's FPGA family or SoC family. By the way, this default value can be changed using EDA tool, electronic design automation tools, GUI, graphical user interface, like Vivado's graphical user interface, or Quartus graphical user interface, or you can change them with tickle scripting as well. So as you may guess, I am not mentioning here that colon equal initial value you add in the HDL code. This is like your tools, like most versions, most vendor tools gives you priority to set default behavior of those flip-flops, which doesn't have any resets, circuitry resets, resetting signal, or default value with that colon equal to. So this is that last bullet explaining this one. So let's continue. Yeah, I provided like 2-3 slides of reset code examples here. So first one is synchronous reset using VHDL. By the way, in general, I prefer VHDL for design and SystemVerilog for verification purposes. And of course, not each and every company follow this type of approach, but it is quite recognized in many FPGA companies in the world. So for design, since by the way, we had in the past lectures comparing and contrasting VHDL, Verilog, and SystemVerilog. So they have all these three have some pros and cons. But yeah, this is the way I am. This is the way of working I am using for design. I prefer VHDL. For verification, SystemVerilog. This is also the current company I am working. This is the approach right now. So of course, that company tendencies are determining these way of workings. So first one, synchronous reset using VHDL. As you see in, this is a single process exempling this synchronous reset. So in the sensitivity list, you have only clock signal. And then you start directly with if rising edge clock, then that clock underscore 400 megahertz, then if this active high reset signal resets RST underscore 400 megahertz, this suffix here purpose is to mention that this reset signal is synchronous to this 400 megahertz clock domain. So as you see, you directly use reset after this if rising edge clock statement, and then you reset the signals you would like to reset, like here my underscore output, that other 0, this is a vector, so all bits are set to 0. Actually this is output port of a test code, and then else that my output, actually this my output internal signal is assigned to my output, so it is registered here. So by the way, if you have any other logic, like some other if statements, some other dependencies, some case statements, etc., whatever you would like to add, you add after this else statement, and you are providing resetting signals that are need to be reset after this if reset underscore 400 megahertz equal to 1 active high synchronous reset statement here. So resetting each and every signal, it is a really bad coding practice. So we will discuss more during next slides. So this is the example for synchronous reset. I think it is clear, but just shoot your questions to the chat window if you have some. Second example is asynchronous reset using VHDL. Yeah, by the way, this one requires a reset synchronizer seen on the bottom right, this one, for each clock domain. I will tell more about this one, but let me first start with the process which has this asynchronous reset. As you see, since it is asynchronous, now you have that reset underscore 400 megahertz signal in the sensitivity list right now. So, and then you start, instead of if rising edge clock here, use in the synchronous one, you start with if reset underscore 400 megahertz equal to 1, then, and then you provide the reset statement. In this case, only my output signal is reset. And then else if you see here there is a priority encoding, so that's active, that asynchronous reset has priority over rising edge clock. As you may guess, it is because you would like to, in case of reset assertion, you want directly to reset the output of these registers, so namely that my underscore output signal or output port, could be output port as well. And then else if rising edge clock underscore 400 megahertz, you register this my output int signal, you connect the my output int signal to my output. So it is like after rising edge of the clock, the values of my underscore output underscore int will be assigned to my output. Actually, it is like after TCO, if there are no issues with setup and hold time here, then you see at the rising edge of the clock after TCO, clock to output delay, you see the value of my output in those registers of my output signal or port. So this is the synchronous one. So these two are simple examples for synchronous and asynchronous reset usage. But as I mentioned here, the second one, asynchronous reset, requires a reset synchronizer for each clock domain. So if, let's say, you have multiple clocks in one entity, you need to synchronize input reset signal to those multiple clocks. Let's say if you have also clock underscore 333 megahertz clock, then you need to apply this reset synchronizer you see on bottom right for clock underscore 333 megahertz as well. But let's see how we are applying this reset circuitry here. By the way, this is also known as AKA synchronous assertion, asynchronous assertion using two flip-flops. So in case your clock speed, depending on your process voltage and temperature, PVT values, and the clock speed, you may need to use 3 flip-flops or 4 flip-flops to get a longer, meaning better mean time between failures. This is the simplest example. So we are using two DFFs, 2 flip-flops here. This synchronizer you're using in the sensitivity list of the process, you are using clock underscore that 400 megahertz and reset. But this time it is the reset coming from some other sources inside the FPGA, which are asynchronous to this clock 400 megahertz, or it is completely asynchronous coming from an external reset IC, let's say. So there is no relation between these two signals, and so you are writing both to the sensitivity list, and then by the way, here in this example, this is a active high reset. So in case of that FPGA, let's say this is an FPGA, one of FPGA's input pins, and that source reset here you are using, it is active high. So then when it is equal to 1, in order to mimic the behavior of this input reset, you apply 1 to those reset synchronizer flip-flops 1, as you see here. And then else if rising edge clock 400 megahertz, then statement, and right now you are providing actually negation of this active high reset. So after assertion, during the assertion, you would like to synchronously change the status logic state of this signal. So you are providing 0 to the pre-register of these 2FF solution, and then assigning this signal here, you see in the 44th line in this example code, to your reset synchronizer output signal. Actually, as you see, we used here this RST underscore 400MHZ signal as asynchronous reset in this asynchronous reset process. So this is the story. If you have let's say 10 different clock domains in your whole design, and you would like to use, let's say, this output, the input reset ports coming from an external reset circuitry from the PCB you are using. And then you need to apply this reset synchronizer for each and every clock domain. Of course, we are assuming here that those 10 clock domains are completely asynchronous. By the way, there is also a nice point. You need to do this reset circuitry, reset synchronizer stuff on the top level. Let me say, making this reset synchronization at the highest level is good, because if you are adding this reset synchronizer in your design hierarchy somewhere in the, let's say, middle or in the lowest level, then you need to do this. You need to duplicate this circuitry in some other parts of the design, and this is bad. Also, there are multiple drawbacks, but let me at least say that it is good to make this reset synchronization at the highest level. By the way, some solutions may require, if you have, let's say, you are using this asynchronous reset approach and you are having some recovery and negative recovery and removal slacks, there are multiple different solutions recommended. So things are getting complicated anyways. So using this circuitry at the top level, this is the best approach. Otherwise, you will add you may add some additional issues. Just ask me. I can draw and tell what kind of negative effects may happen. Ask those detailed questions during the Q&A session on Sunday. So this is the not using reset example, no reset with VHDL. So it is assigning initial value via this colon equal operator. So you see, it is I provided the screenshot of the entity. You see there's a clock, 400 megahertz clock input. So there are multiple inputs underscore 1, 2, 3. Input 1 is a STD logic vector. Output is also, my output is an STD logic vector. Both lengths are depending this generic data with generic. So initial value of this generic is 32, but it may of course changed from the higher level with a generic map. Sometimes it is 128, sometimes it is 256, something like that. So it may change depending on the use case. But here, some little bit below these lines, we start our architecture with architecture statement, and signal declaration is here. Actually, the length of this STD logic vector is determined by this input underscore 1 vector using that range attribute. So it is actually it is the same as writing data with -1 down to 0, but you see it's a little bit shorter. We are using those VHDL attributes. One of the VHDL attributes. This is also really nice. This range attribute is really nice for loops. Also, there is that reverse range attribute if you are using some for generate, if generate statements together with some loops. Also some loops to implement some part of the design multiple times depending on the size of this the STD logic vector you are using. So for instance, if you use reverse range, then if it is, let's say, 7 down to 0 kind, then reverse range is 0 to 7. And for those for loops, it is usually preferred to use that 2. So it is ascending order. Descending is this down to. So for the logic, for the input output ports, we prefer those descending one in VHDL, like most of the time. But for loops and also for arrays, those 0 to something, I mean those ascending order is preferred. Here you see, for instance, we would like to set an initial value with this colon equal. We used another attribute like input underscore 1 left. So designer would like to assign most significant bit of this my signal 1, so that most significant bit is 1 and others are 0. You might also use like input 1 left minus something to set some other parts of this vector. Also, you might use other attributes like right to go to the least significant bit. So this initial statement, the others will assign all the bits to 0 here in this example that are not specified. So like if we didn't write this input underscore left equal, actually this assign what was this arrow in VHDL, that's 1076 document, it's called arrow. So this arrow operator, if we didn't write this one, then all bits would be set to 0. But since we would like to assign 1 to most significant bit, we used this statement. Also, for instance, you could write 3, so the least significant 4th bit, like 5 least significant 5th bit. You could write, instead of input underscore 1 tick left, you could write 5 directly. But it is usually not preferred because, you know, it is like a magic number. So instead, I prefer, if I would like to that right left plus something minus something, I prefer that way. But it is not that bad, let me say. So here, as you see, in the sense, since it is not it is not asynchronous, that clock is not in the sensitivity list. But since it is not also synchronous, we don't have a synchronous reset. We don't have that if reset statement after that if rising edge clock statement. So this process, as you see, p underscore no underscore reset, it just registers this my output int value. So with 1 clock cycle latency, all the contents of this my output its signal is assigned to my signal. Okay, I think it is fine. Just ask your questions if you have. So this was the end of reset code examples part. Now reset architectures, we will focus more on reset architectures and infrastructures. Actually, I tried to like summarize some critical points that I learned during my 15 years of FPGA engineering. But this is a huge topic. Let me say, if we sit like 4 or 5 engineers and chat about this issue, it may take like 4 hours, 5 hours. It's a long discussion There are many pros, cons, drawbacks, some benefits sometimes, but sometimes it has some negative impacts as well. So this is not a let me say easy concept. By the way, I trust my knowledge about these reset architectures, infrastructures, usage, because I have worked in many projects. So you need the experience working with different vendor FPGAs, let's say. Not only vendor, but also family of FPGA families of same vendors are also behaving differently in terms of this reset usages. So you need to work in different projects with smart engineers, preferably in different companies. Then you will get you will learn those details, pros, cons, in this long run. So it is not, you cannot, for instance, be in my opinion at least, very good at in these reset architectures, reset usages, those generic designs, depending on the FPGA vendors and families, in a few years. It takes some years. Also, it is not enough to be smart. Your colleagues shall be smart as well, should be smart as well. Also, your company should provide you some good projects. I think combination of these will make you really a senior or expert in this topic. Actually, it is, in my opinion, similar in FPGA design and verification as well. So you need to, of course, work hard, but you need to have those prerequisites as well. So let's continue. Vendors, FPGA vendors or SoC vendors, you know, those are called SoCs when there are hard CPUs in the same fabric as well. So new trends are those system on chips. But when I'm mentioning FPGA here, I'm mentioning all those. So majority of rules here also apply ASIC design. But ASIC design is actually ASIC design contains more steps, because at the end, most of the time you are doing mass production. Some additional special stages exist in ASIC design, application specific integrated circuit design. But philosophy, the ideas lying behind ASIC design is also similar. But let's continue for FPGA case. Vendors recommend to take special care in deciding if the design requires a reset. So as I mentioned like 5-10 minutes ago, applying reset to each and every signal you declared you are using in your whole design is really a bad coding practice, and it has lots of drawbacks. I will mention some of them during this today, let me say, in the incoming slides. So you need to design reset architecture very well as well. I gave one example. If you do those, if you need to use some asynchronous resets, it might be because your company prefers it, or some system requirements, some architectural decisions end up with such usage. Then you need to do that reset circuitry, that synchronous assertion, asynchronous assertion, synchronous assertion circuitry at the top level, and you need to think about it. You need to, at the beginning of the project, let me say, using that 8-step design and verification approach we discussed during the first lecture of this series, you need to foresee. Of course, 100% foresee is not possible, but you need to think what will be the fanouts of those signals, what will be the number of clock domain, what will be the number of reset domains. So you need to work with some experienced engineers as well. Otherwise, you may not guess such negative drawbacks, and as the design becomes bigger and bigger, you will get some resource usage, some timing closure issues, and the solutions are really getting more and more complex, more and more harder if you don't foresee such effects at the beginning of your design. So let's try to give some examples. Yeah, as I mentioned, you need to design reset architecture very well, otherwise it will result in many design and verification optimization or complexity issues. Actually, it is affecting verification as well, since those multiple reset domains, multiple clock domains, complicated, highly valued designs, they are all tough in terms of both design and verification. So it is not the problem of only design engineers. In many situations, resets are only required on the critical control path logic for proper operation. So such as finite state machine signals, clock enabled signals, data valid signals that are using in your entity, in your design. Of course, you have a top level and you have multiple, sometimes let's say hundreds components, maybe more components in your design. But you need to think about this, that signals that are not affecting any output signals, when they are not reset, you shall not put them in your after your reset stage. So it doesn't make any sense to reset all those signals in your design. Saying this because I have, like in 15 years, let me say, majority of, like more than 90% of the designs I have handled, I have edited all those signals declared in an entity. They were reset either using a synchronous or asynchronous reset. So this is a bad coding practice. By the way, Xilinx, you know, it is one of the leading FPGA vendors. So they are quite popular. I think it's a great company. Xilinx states that since 2006. So it is not a new thing. But unfortunately, majority of the FPGA engineers, in order not to take any risks, they were just resetting all the signals. Either using, some companies prefer more synchronous resets, some asynchronous. Sometimes there is a logic behind, sometimes there is not. But that, as I said, majority of the designs I have seen, they were resetting all those signals. So this is a bad coding practice. And as you like start using 30-40% of the FPGA resources in terms of lookup tables, in terms of DSPs, in terms of flip-flops, in terms of RAMs, so memory elements inside. So this getting a bigger and bigger problem. And as I mentioned a few minutes ago, it becomes really extremely hard to solve at the incoming stages of the projects. Actually, this is one of the reasons why some projects are impossible to freeze and stop. because they are not properly designed from the beginning. So because those requirements of the designs were not clear, etc., etc., there are multiple reasons. But that's not properly doing clock domain architecture and reset architectures. This is also one of the major reasons, because you cannot close the timing, so you have some negative setup slacks or recovery slacks if you are using asynchronous resets. And yeah, routing is getting harder and harder. Placement is also affected. So yeah, if you are using resources of your chip from the beginning, and if your company, your team doesn't have a very well optimized IPs that are really reusable, then yeah, anyways, after like sometimes after 6 months, of sometimes after 1 year, you start to face with such really complicated issues in your design. So this statement is quite strong. Let me read it again. In many situations, resets are only required on the critical control path logic for proper operation. So those, what are those critical control path logic signals? Like finite state machine signals, clock enabled signals, data valid signals, or output signals. By the way, not all output signals that are coming out of one of your entities, sometimes they are also not affecting an output from FPGA pins directly. So you may skip some output signals as well. You may skip some data valid signal as well. So you need to think about it. You need to discuss, do some brainstorming regarding these with your team. So if you start optimizing like this from the scratch, or if you learn these approaches at the beginning of your career, then in like 5-6 years you will be, as you also experience working with different FPGAs, different vendors, different families, then you will be quite strong regarding this. So this is the key for this issue. So next statement, flash-based FPGAs require additional attention, since I mentioned a little bit at the beginning, their flip-flops does not start from zero like RAM-based FPGAs, but start from last value they got just before previous power off. So they are like non-volatile memory. So if you don't use reset statements, either synchronously or asynchronously, then they will keep their last value before the previous power cuts. So then with that initial statement, colon equal operand we mentioned, we are using that the end of that signal declaration or variable declaration. So it doesn't work in that case. So this is again an important difference between flash-based and RAM-based FPGAs. Also, some mission-critical signals or potentially dangerous hazardous signals. For instance, a laser designation signal. So some of them are not eye safe, and in some conditions, let's say user might want to stop that laser designation with a, you can do it by the way properly, this one with the asynchronous reset, because one of the drawbacks of synchronous reset compared to asynchronous is that there are many pros and cons for both. But if you are using synchronous reset and let's say your clock circuit is gone, somehow you cannot generate a clock. If you don't have a clock source, since that process is triggered only at the, let's say, rising edge of the clock, and if clock is all continuously 1 or continuously 0 due to a problem, then you cannot reset that laser designation signal. So for that hazardous signals, dangerous signals, or some mission critical stuff, most of the time asynchronous reset is preferred. On the right, actually you see design assurance guidance, a summary of design assurance guidance for airborne electric hardware. So you know, the majority of you probably know that abbreviation DO254 by RTCA group. So it's a committee. I think it's radio telecommunications kind of committee. I don't remember that abbreviation by heart, actually open form by heart, but yeah, for instance, this DO254 has different design assurance levels. So higher DLAs require more rigorous process, as you see. For instance, that level A is cartographic, then yeah, it could, for instance, you see here some descriptions: failure causes crash or death. So then you need to consider all those complex scenarios, all those worst cases, like example systems flight control here, as you see. So then you may need to, for instance, asynchronous resets, though you are not supposed to use asynchronous resets if it is not a level A DO254. So this is an example where, in case the level of this design assurance also affects your design strategies. I think that is also fine. I have 2 more slides regarding reset architecture and infrastructure, but it is here 9 p.m. in Turkey. I think it is 11 p.m. Let's have a 5-minute break at this point. Then I will continue with the following slides. So I think I have 5-6 more slides, and then I will have the wrap up and check the questions in the chat. So let's have a 5-minute break. All right, I am back. So let's complete those last two slides regarding reset architectures and infrastructures. Let me a little bit increase the size of my video. Okay, let's continue. So EDA tools that detect clock domain crossing, so abbreviated as CDC, have become a standard quality check in today's designs. For instance, yeah, I am using, actually I had many great experiences in Questa CDC in this year. At ASML, I used that tool extensively. I told, actually that tool helps you to diagnose those clock domain crossing issues in complicated designs. But solutions, you need to provide those solutions. Yeah, there we also discussed a little bit in the previous in English, also in Turkish lessons, lectures we had in this series. But we will also be discussing them in the next classes as well. But yeah, that tool is pretty sophisticated, let me say, and you are applying those clock domain crossing checks analysis. You are adding them to your CI/CD pipeline, and every time design checks, actually daily, weekly, and monthly, those tests are applied. So as you yeah, it is that daily tests are a little bit less complicated, but still checking some stuff. Weeklies are more complicated, and monthly, once per month ones are the most complicated test scenarios. So, but newer to the game, reset domain crossing RDC verification is also in last 4-5 years, maybe 2-3 years. Of course, it depends on the company. Maybe you are not using any RDC verification in your company, but they are also getting quite popular because, as I mentioned, in some designs, like the one you see on the bottom right, you need to use, due to some requirements, due to some architectural decisions, you need to use asynchronous resets. And if you are using only one reset synchronizer for each clock domain, the fan out of those reset signals are going beyond 10K, more than 10,000 fan out, let's say. And then you are starting to get negative recovery and removal slacks. Also, yeah, that it also increases that routing complexity. So some you need to use all the time those global routing paths and those GSRs, global set resets, IPs, together with that high fan out, and it results in some problems. So in order to solve it, actually you are in the same clock domain, you are using multiple reset signals. Like you see here on the bottom left, there is only one clock domain. These two flip-flops both are using that clock signal, but the data source of the second one is that DFF1, but it is clock is something different. It is reset is something different. So reset 1, it is asynchronous. Problem here that you need to take care of this harmony between those two clocks. Let's give an example. If this reset 1 is active, since it is asynchronous, you know that assertion is asynchronous, and immediately the output of this DFF1 will be if it is reset value, its reset value is 0, then it will be 0. But if this second flip-flop is not in the reset at the same time, then setup hold violation may occur in this data path, because if this second flip-flop, the one on the right, keeps working, you know, at the rising edge of the clock, this DFF2 will try to sample this data you see in the middle, and then setup or hold violation may occur. So, and static timing analysis cannot guess that. You know, it is static. So here scenario, due to the scenario in the real system, some dynamic changes occurring. So this reset 1 is reset, but it is somehow not propagated to reset 2. And then the output of this DFF2 might be metastable, and you may get corrupted results. So, by the way, these RDC tools, Questa also, actually Mentor Graphics also has that Questa RDC tool. It provides solutions to a couple of problems, but one of the major, one of those major solutions is this one. So tool actually checks those dependencies of asynchronous multiple clock domains, and then suggest you actually tell you to solve those issues you are solving. Again, there are some actually, of course, some solution recommendations, but you need to take care of them. But if you are using only one clock and that asynchronously asserted, synchronously deasserted one reset signal, probably you are ignoring your negative recovery and removal slacks in a complicated design. By the way, it is really bad as well. If you have negative recovery and removal slacks, and after each power up, after each reset on the system, you will be observing some unexpected behavior. For instance, you will power on the system, the reset chip in your design will trigger a reset signal after the power on, and if you are having if your design have negative recovery and removal slacks, since you are using an asynchronous reset, then it is also a big problem, because then each and every signals that are changing its state after the assertion, the assertion of the reset, then you might have those unexpected behaviors as well. So since those SOCs are coming to actually going into many new designs, they have lots of flip-flops, lots of resources. Also, they are communicating with like those ARM CPUs, also those RPUs. Those scenarios are getting complicated and complicated. So these RDC tools are really beneficial, essential for complicating a complicated FPGA and SoC design. So keep in mind this one. As it is stated in this bullet, improper reset domain handling can cause metastability issues. I gave one of those examples here, and unpredictable behavior as we see in clock domain crossing errors. So it is as risky as that one if you are using resets improperly. So we discussed these examples, but here there is another strong, more general statement. Applying synchronous or asynchronous or synchronous reset to all the signals in the entity is a big waste anyways. Even if the vendor technology has dedicated, in other words, built-in asynchronous or synchronous reset pins, there are some drawbacks such as routing congestions, extra power usages, etc. Also, yeah, as I mentioned during the first part of the lecture, it increases verification complexity as well. So try not to use resetting for each signal as much as possible. But when you need them, when your team architects, train architects, or system architects ask for it, then use it. Don't decide. Of course, by the way, as a designer, you can take responsibility and say that, okay, I need to reset this counter because this counter is critical for me. So it is not, it shall be reset in my code. You can make, of course, this decision. But sometimes, yeah, those you may not foresee its drawback. So it is really, really helpful to get design reviews for your colleagues as well, from your colleagues as well. So sometimes inexperienced ones, sometimes experienced ones, they can see such bad coding approach and give you proper feedback regarding that. So this is also really helpful. Also, as I mentioned, these RDC, CDC tools are great. Plus you are using linting tools. So both manual and automatic checks are ongoing, and then that quality of the code, it increases dramatically. Otherwise, if you are miss some of many of these essential solutions, then instead of like 9 out of 10, your design quality becomes 3 out of 10. So you need to benefit from your company tools, your colleagues, and those new approach, new tools that are popular for those complicated designs and verifications. But avoiding the unnecessary use of resets provides us some nice stuff like these. They limit, actually avoiding limits the overall fan out of the reset net, as I mentioned. So even if you are using one and only one reset synchronizer for each clock domain, if you skip those unnecessary signals that shall not or not necessarily reset, then you can reduce the fan out of the net. Then you can close timing. You may in this way positive recovery and removal slacks in the scenario that you are using asynchronous reset, for example. Also, those avoiding unnecessary use of resets reduces the amount of interconnect necessary to route to reset. Usually global routing paths and those global set reset primitives are used if you have that intensive use of extensive use of extra usage of resets. Avoiding those results in this nice positive thing. Also, it simplifies the timing of the reset paths and reduces the total static timing analysis STA effort and time. So that tool easily meet the timings. Also, that full compilation time may reduce sometimes dramatically because static timing analysis effort is less. Therefore, it takes much less time. to complete this STA. Last but not least, it results in most cases in overall improvement in performance, area, and power usage. So you are winning if you avoid unnecessary use of resets. You win actually in terms of many things. Like you use less resources, you use less area, also power usage is less. Then your chip, either it is SoC or FPGA, it will heat up less, and yeah, you will not exceed, for instance, those extreme temperatures. Like let's say if it is a automotive or what was the other one? Let's say automotive FPGA speed limit temperature limit minus 40 degrees Celsius to 100. So then it, let's say, instead of 5 hours of extreme usage, your design, your chip may work for, let's say, 15 hours or more. Because if your chip heats up fast, and if in most of those embedded designs there is no air conditioning unit. Sometimes some really expensive and complex designs include some air conditioning units, but they are also not capable of cooling down each and every chip inside an embedded system. So designing in an optimum way, optimizing performance, area, and power usage will help you anyways. So some pros and cons. Was it 2 slides or? Yeah, 2. We have 2 more slides. So asynchronous reset versus synchronous reset versus not using reset. Actually, preferring synchronous or asynchronous resets depends very much on the specific vendor and family you are using. Requirements are important, as I said. If you have a like that hazardous, dangerous laser designation signal, anyways, you may apply asynchronous reset for that. That is fine. But for the general way of working during the design, preferring either synchronous or asynchronous reset depends on your FPGA vendor. Let's say it is Xilinx, and the family, let's say Ultrascale plus family. So it is important that FPGA families that are being used also maybe sometimes target families for future, the ones you would like to use in the near future or in mid-range. They shall be investigated and learned very well. Otherwise, if you are not using capabilities of your chip, of your FPGA family that are using, then you cannot do an optimum design for that one. Afterwards, design shall be implemented accordingly. So according to capabilities of your chip in use. For instance, one good approach, actually I follow this approach as much as possible as well. You need to have generics selecting your vendor. Let's say it is selecting either it is Xilinx, either it is Microchip or Altera. And then one more generic, it is the family generic. Because you need to select, let's say if the vendor is Xilinx, then you need to select either it is Vertex 4, either it is Vertex 5, or Vertex 7, or Ultrascale Plus, or Versal. So those different kind of families, and huge companies usually have many legacy designs, and you need to take care of different, sometimes 10, 20-year-old designs. So you need to go this way. You need to have vendor and family generics, and then generate if statements and specific optimizations for each family. This is, by the way, similar for DSP usage in FPGAs as well, because each family, newer families have wider input vectors. They, for instance, newer FPGA families are capable of, instead of 18 by 18 multiply and sum operation, they could do 27 by 18 kind of, or larger ones. So you need to optimize your code accordingly. This is multiple vendor and family generics, and then generate if statements. This solution is really optimum. I really like this way of working. I have two nice examples here. For instance, slice. By the way, Xilinx call these slice, FPGA slice. Altera calls ALM, adaptive logic modules. But slice or ALM register, in other words, flip-flop examples for some Xilinx Altera FPGA families on the left side, left bottom. Vertex, for instance, Xilinx Vertex 567 families have slice registers with both built-in synchronous and asynchronous reset pins. But note that majority are synchronous. On the other hand, Altera, Stratix 5, Cyclone 5, Cyclone 10 and Arya 10 families have ALM registers with built-in asynchronous reset pins. So, then in terms of performance, for instance, for the ALM registers, using built-in asynchronous resets with, as I mentioned, proper reset circuitry, plus taking care of those possible high fanouts with resets, possible recovery removal issues, by handling that, using asynchronous reset prevails in Altera, those Altera families, for instance. Because otherwise, if you use synchronous reset, then one input of lookup tables in your design resources are used each time. So let's say if you have a 6 input lot technology, then one of those 6 input lots will be used for resets, since it is synchronous reset. There is no dedicated built-in reset pin. Then it will, by the way, it is decreasing Fmax. Let's say you have a Arya-10 family and you have written an algorithm that needs to work in 300 megahertz. You can make it run like this with built-in asynchronous reset pin in 300 megahertz, but it is nearly impossible to do it if it is like a little bit complicated design with some arithmetic operations and some checks, if statements, else statements kind of logic. So then I tested, by the way, these in the past. Then it is working like in 200 megahertz because that one of those 6 input lookup tables is used, and actually you are working as if it is a 5 input lot technology, lookup table technology. DSPs, by the way, similar example, but for DSPs this time. DSP register flip-flop examples for some Xilinx Altera FPGA families. Xilinx Vertex 567 families have DSP registers with built-in synchronous reset only. For instance, in this case, if you apply some asynchronous resets in Xilinx FPGAs, and then an emulation circuit is applied, and all those reset stuff cannot be handled in the internal registers inside DSP. Then let's say instead of working at 400 megahertz, using a DSP. If you are applying asynchronous reset, then it works only 250 megahertz, for instance, 250 megahertz. There is a dramatic speed reduction. Altera, on the other hand, Altera Stratix 5, Cyclone 5, Cyclone 10 and Aria 10 families have DSP registers with built-in asynchronous reset pins only. So as you see, it is not that straightforward. So for instance, Stratix 10 families, one of those newer families of Altera, they have much more built-in synchronous reset pins, unlike previous generations. So you need to read the documentation of the FPGA family you are designing, you are working in each project, and then you need to do your design accordingly. It's not also include reset strategies, but also design strategies as well. You need to know how many you need to know capabilities of your slice. You need to, or ALMs, you need to know capabilities of your DSPs, those multiply and accumulate operations, also those always inside capable of arithmetic logic units, capable of doing many things. So you need to know and design according to the FPGA families you are using. That is really important. So some more compare and contrast here. Using asynchronous reset brings recovery and removal time issues. We discussed this. Additional metastability issues you see. In order to minimize, actually in order to solve those high fan out issues, because high fan out is really bad, because that routing congestion starts. So in order to get positive recovery and removal slacks and reduce the fan out, so gets easier routing, you may have multiple reset circuitries for asynchronous reset. But then, as we give example in the RDC part, you are getting additional metastability issues. So also potential reset or ordering problem. That order of those resets are important, because as we gave example, as we illustrated there, if you reset the source data source flip-flop while that flip-flop capturing the data is working, then you are also getting some metastable outputs. Also, one other general drawback of using asynchronous reset, some noise or glitch in the reset may result in resetting everything, all those signals connected to the reset, because you know it is asynchronous. So it is not checking, it is for the synchronous reset that shall be active, of course, by properly holding setup and hold constraints, but it is sampled during the rising edge of clock. But asynchronous ones, as soon as you get a small pulse of glitch, a small glitch, let me say, and then all those processes using asynchronous reset will be reset by, and those values you provided inside that if statement. So it is a little bit risky. But sometimes also, let me mention, for the synchronous resets, you may need to stretch those resets, because additional circuitry are used in order to stretch those internal reset signals, because they may not be captured with different clock speeds. So, but anyways, you need to, those shall be synchronous. So there are some easy solutions for stretching those clocks for resets for synchronous reset usages. A drawback of synchronous resets, actually it is a major drawback, as I mentioned during the previous slide. If your FPGA family does not have that built-in reset pin, then you are wasting one input of your lookup table. And then timing closure, in parentheses, that maximum frequency issues becomes you are getting some negative setup and hold selects. Actually, Fmax only setup time is dependent on the frequency, so you will have let me tell it again. Setup slack calculation includes periods, clock periods, but hold doesn't. Hold is a little bit more tricky, so we may discuss. Also, we discussed those during our Turkish lessons, but for the English one, we will be also discussing during some timing classes. But wasting one of those inputs of your lot results in lower maximum frequency, and if your constraint is a little bit tough to reach at that technology, let's say it is Vertex 7 and you are trying to run a complicated design at 400 megahertz, then that synchronous reset also results in some bad timing. So you are getting some negative selects. For instance, it works only at 365 megahertz, kind of. You need to, as I mentioned, remove unnecessary signals from your reset bed as much as possible. So as a conclusion, therefore, unless you know FPGA family technology and design accordingly, if you don't do this, if synchronous reset is used, a reset emulation circuitry is applied. So you are using some extra resources. For instance, yeah, they are in the slice or ALM. It is extra bad if that asynchronous reset is applied to DSP signals. Then that timing will be worse because you need to emulate that reset circuitry outside the DSP. So this is bad. And as we mentioned above, if synchronous reset is used and one input of lookup tables with related signal is consumed. So both are resource waste. Yes, this brings us to the end of 9th lecture. I will check the questions, but let me thank everyone that have followed this lecture, and I hope to see you this Sunday morning, so 1st of December, in the Q&A session. I will be very happy if you can like the stream, and you may share the link of this lecture people who may interested in with this content. So thanks a lot. Now let me refill my coffee and I will be checking the questions. Okay, then I can make myself full screen. Yes. questions. Okay, Mehmet Ali has one question. He says, if we have a long time duration reset signal, could not use any reset synchronizer, just drive async reset through on blocks. If we have, okay, let me try to understand this question. If we have long time duration reset signal, so saying that you have a signal that is resetting your system for a long time, couldn't use any reset synchronizer, just drive asynchronous reset through on blocks. No, I got it. So Mehmet Ali asks, if you have a quite long amount of time reset, is it possible to not use any reset synchronizer, just drive the asynchronous reset directly? Actually that the time your system is on reset has no effect on the possibility of the metastability, Mehmet Ali. So even if either it is 10 milliseconds or 10 seconds, it doesn't matter. Problem is with the assertion, not assertion. Assertion is not a problem because during, let's say you have an active high reset. By the way, active high is preferred because then during that functional time that your design works, the reset will be low, and then that probably highly probable high fan out signal will be logic 0 for a long amount of time. But for the, if you have an active low reset, then it is reset for, let's say, 300 milliseconds. Then for 3 hours, 4 hours, it will be 1. And then that high fan out signal inside FPGA is kept on VCC, so logic 1. Let's say it is 1.8 volts path. Sometimes, by the way, it is 2.5 or 3.2 volts as well. So it is really bad coding practice to have active low reset inside the FPGAs or SoCs. Even if the outside reset is active low, you can just negate it and use inside FPGAs. So you need to, of course, be careful. It is not that straightforward, but solution is easy. This is one thing. But let's come to your question. The length of the clock, it doesn't matter. During assertion, if it is asynchronous, it is directly, those signals are getting reset values. But while going out of reset, if you don't have that reset synchronizer, then that deassertion, synchronous deassertion would be a problem, could be a problem, by the way. And then your output registers could be metastable. But there is one nice condition regarding that. It is happening when reset value and out of reset value of your signal is different. For instance, if you can guarantee the reset value of your signal, let's say you have a signal Mehmet underscore Ali. Let's say name of the signal is Mehmet underscore Ali. Okay. And that signal, you reset it with asynchronously and set it to 0. And you know that in your design functionally, after reset the assertion, it is not possible that that signal would be 1 for a long time. For instance, you are waiting another trigger, like let's say a frame signal, frame valid signal. So if in the code of else if rising edge clock portion of your process, if the next state value cannot be 1, then there is no possibility of metastability in this case. So due to that negative recovery slack. But it is really in complicated designs. You cannot guarantee that you need to. For instance, design is most of the time not only your custom code. You are reusing some IPs. Also, you are using some vendor IPs like those Quartus, for instance, and Vivado soft IPs, Microblaze, sometimes RISC-V, Microblaze 5s, also Nios 5. So there are many also codes that you are not in control 100%. Also some parts of IP that are written by your colleagues or ex-colleagues in the past. So if you like ignore that probability, then that finding the bugs related to this kind of issue will be really almost impossible. So that is why all those experienced designers always close timing with positive setup and hold slacks, and also positive recovery and removal slacks. You need to provide that reset synchronizer. So I think it must be clear, but if you haven't understood, please ask again. Thanks a lot. By the way, all those guys commenting in the chat, they are quite brilliant, hard-working FPGA engineers. Thanks for attending. Yiğit, Mehmet Ali, Mert, Furkan. Keep working like this. So you will be great engineers in like 4 or 5 years. Just keep working like this. Of course, as I mentioned, you need to have good teams as well, and you need to work in a good company which provides you some good infrastructures like projects, tools, etc., licenses, etc. Okay, I think, by the way, you may ask your questions during the Q&A session this Sunday as well. So, like, we are coming close to 2 hours. I think this is a good point to close this lecture. Thanks a lot. Have a great evening or night. Hope to see you this Sunday at 10 a.m. European time and 12 p.m. So like just the noon in Turkey. Thanks a lot and take care. Bye bye.